Okay, good morning everybody. Nice to being here. Today I will give you a technical training and an overview of our product range of the energy harvesting switch. We start with a technical training with basic informations about RF and RF parameters. The second part will be an overview of the product range with the special parameters of the product. And at the end, I will give you some descriptions of the receiver pairing and the handling of the receiver. Okay, let's start with the technical training of the RF parameters. I give you an overview of the most important parameters which are important for an RF system. Because you will see at the end, to design an RF system which covers all the environments and all the requirements from customers or markets is not possible. You will see it at the end. An RF system can only be designed to one special use case, and for all the others you have to make compromises. A later part I will give you some informations of the interferences to an RF system and how can we avoid such interferences, and at the end a short overview of all the approvals, because of you need for RF systems in every country of the world a special approvals, and I give you an overview of the most importance. Okay, let's start with the important design parameters. As you can see here, there are some special parameters for an RF system which are much important for it. This is, for example, the frequency, the RF frequency where you send out the signal. Then it's important the data rate. The data rate we will see later is the speed, how fast the data will transmit it over the RF channel. Or the protocol. The protocol is the language between the sender and the receiver. The telegram length depending on the protocol. The transmission range is a physical parameter of the designed RF system, and the antenna is also a very important parameter. Let's start with the frequency. Frequencies for RF systems are regulated by the so-called ITU. The ITU is the International Telecom Union, and they defined all RF bands. They call it bands. Yes, a band is an area of frequencies in which you can take your special frequency for your RF systems. And the ITU defined different frequency bands all over the world. You can see here they divided the world into 3 areas or regions. And they say, okay, in this region you can use these frequencies. For example, they decided that for the region 2, it's North and South America, you can freely use a frequency in the band of 902, between 902 and 928 megahertz. And you create an RF product, you can use a frequency in this band. So when we speak about 950 megahertz protocol or 868 protocol or 2.4 gigahertz, then we always mean this band. But 950 is the center frequency in the middle of this band. And so we say, okay, it's a 950 megahertz. But it's always a band. You can use one frequency of this band. Another important frequency for us is the 2.4 gigahertz. And you see here, 2.4 gigahertz is a worldwide free frequency. And this is a very big advantage of 2.4 gigahertz. The ITU said if you use 2.4 gigahertz, a frequency in this band, 2.4 gigahertz band, then you can use this product worldwide, region 1, 2, and 3. This is a very big advantage. So I have to design a product with one frequency, and I can sell it all over the world. We will see it later. Okay, I need an approval in every country, but I have to design only one time my product. If I design a 950 megahertz, then I will get a problem. because 950 is only for region 1. If I want to sell it in Europe or in Asia, then I will become a problem. Especially for Europe, the European Commission said, okay, for Europe especially, we create another band. It's called the SRD 860 band, and it's a band between these two border frequencies, and the center frequency is the 868 megahertz. So we called it 868 megahertz band. And this is a special frequency band we can use in Europe. So now we have 3 frequency bands, 950 for USA, Canada, South America, 2.4 gigahertz for all over the world, and the third one, 868 megahertz for Europe. And this is the reason for why we use different RF frequencies. The best solution would be we use one RF frequency, design our product with one RF frequency, and sell it all over the world. But you see here, regulations said, okay, that's not possible. 2.4 gigahertz we could, but we will see later, a 2.4 gigahertz had some physical disadvantages against these frequencies. And in China, it's completely different. China divided not into frequencies, China divided their range into products, different device categories. And they said, okay, we make a list of different device categories, and every device category can use a different frequency. So, and we find a device category where our product fits in, and you see here you can use different frequencies, for example a 433rd frequency, but we don't have such a product, so we go to the regulation committee, the SRRC it's called in China, and say what is about 868 megahertz or 915, and they said okay, you can also approve products to this frequency. So China is more confusing than the other countries, no such regulations. So, but it's possible, so it's very easy for us. We don't need to design another frequency, we can use our products and can get approval for the products also in China. The design parameter frequency, so I said, you know now 3 frequency bands we are using with our products. The 868 megahertz for Europe, the 950 for US and Canada, but this is depending on regulations. And the 2.4 gigahertz worldwide. So why we don't use 2.4 gigahertz for all our products? It would be the easiest way. We can sell it all over the world. And this is one disadvantage of 2.4 gigahertz, because the physics says to us the higher the frequency, the lower the physical transmission range. That's a physical law. So this means the higher the frequency, the lower the range. 2.4 gigahertz is a much more higher frequency as 915. Therefore, the transmission range, the physical transmission range is lower. And here you can see some examples. The transmission range and the frequency depending with the wavelength, but it's not so important. When you here see the physical transmission range of a 2.4 gigahertz system is 177 meters. You can type all these parameters in a physical formula and then you get out this transmission range. For a 950 megahertz system you can reach 464, and for 868, 488. And this is much more wider. So here you can see a very big disadvantage of 2.4 gigahertz frequency. From the regulation side, it would be a very good frequency. We can use it worldwide. We have to design one hardware. We can sell it all over the world. But from the physical side, it's a very disadvantaged frequency. And this does mean when you design products, for example, for in-room communication, a light switch who sends a signal to a bulb or to a light, to a lamp, then it's no problem for 2.4 gigahertz, it will work. But when you want to send your RF through a wall or through two walls or through a ceiling, then you will get a problem with this. Then the transmission range of such sub-gigahertz frequencies is much more better. So that is what I said, it's a compromise. Yes, we cannot design an RF product for all requirements and for all use cases. The next design parameter is the protocol. The RF protocol is the language between the sender and the receiver. It's the same between us. English is a conversation language between us, but in Germany the people speak German with each other. It's another language, and it's the same in the RF world. There are different protocols between sender and receivers. And on the market, when we started with energy harvesting and RF products, every week we found a new RF protocol on the market, a new standard RF protocol. And we said, oh, it's so confusing. What is the right one for us? And with the time, we get a feeling what are the most important RF protocols for us will be and for our products. Yes? And so we reduced all this different product to the followings. ZigBee is a very popular RF protocol in the United States. Also, it will become more and more popular also in Europe. Ocean is also a very, very popular RF protocol concerning energy harvesting. Everybody of you know it, energy harvesting, Ocean. Then we create our own ZF proprietary protocol. We said, okay, let's make a very, very short protocol for our energy harvesting system. And in Europe, there is a standard protocol for home automation, building automation. It's called KNX. Former, the name was Connex. It's most popular in Europe. It became popular also in China and also in the US. And the RF protocols are depending also on the frequency bands. The ZigBee standard is made for the 2.4 gigahertz frequency. So in the past, they decided the community of the ZigBee Alliance, let's make a ZigBee protocol and let's make it for 2.4 gigahertz frequency. For the sub-gigahertz and Ocean, 868 megahertz they use in Europe, okay, but in the States they cannot use, though they have an alternative to 950. And also ZF protocol, we created to 868 megahertz and also an alternative to 950 megahertz. And the KNX, for example, is especially for 868 megahertz at the moment, but when they will spread out it, for example, to the USA, they had also to use the alternative of 950 megahertz. So protocol and frequency are combined together. For example, Bluetooth, oh, you can see it on the slides. Here is Bluetooth low energy. It's also a 2.4 gigahertz protocol, but I shift it out at the moment because currently it's not an issue for our products. Okay, what is so important on an RF protocol for our products? RF protocols define so-called telegrams. Telegrams, you can compare it with the words in our language. We have long words and we have short words. And for communication, we need a sequence of words. We create sentences. And in an RF protocol, it's nearly the same. They define a communication standard or a communication sequence. And the minimum length of words in RF world is telegrams is wrote down here. For example, KNX telegram length. Is there also a pointer inside? Yes. Telegram length you can hear is 35 bytes. Bytes is the number of data inside. ZigBee you can see is 21. It's not so long as KNX. Bluetooth is 17. It's shorter than all these. And Ocean you can see here is only 14 bytes. So also Ocean creates a very slow telegram, especially for energy harvesting systems. Okay, and our protocol, our ZF protocol, is only 12 bytes. We create our special protocol and say, okay, 12 bytes is enough. So when you think about it, 12 bytes, but we only want to transmit a status of our switch. Yes, for example, when you press the switch and when you release the switch, it's only one signal. Why I need 12 bytes? It's only one bit. I can use only one bit. If it is high, I press. If it is low, I release the switch. So why I need 12 bytes? And this is also a physical reglementation of RF. You need a special design of your RF protocol that it works over the RF channel, that receiver and sender understand each other. And so, for example, at first you need a so-called preamble. The preamble is the introduction sequence of a RF protocol. Yes, it's because of when the sender sends out an RF signal, yes, then the receiver catches all the signals on this RF channel. So it does mean if other sender uses the same RF frequency channel, the receiver gets all this information. And the receiver has to divide what information is for me, what is important for me. And for this, the preamble is the right thing. On the structure of the preamble, the receiver knows, oh, that is a signal for me. It's from the cherry switch or a cherry sender. Then after the preamble, there comes a sync word. It's a data structure that the receiver knows, okay, now the data starts. After this sync word, the data starts. And the data of our protocol is the unique ID, 4 bytes of unique ID. We will see it later why it is important. And only 1 byte for a switch state. Here it is. Only 1 byte. And 1 bit inside this byte is for the switch state, press or release. And at the end of the telegram, you need a CRC. It's a check to detect errors in the telegram. So you see, it's not so easy to transmit data over a RF channel. You cannot use only 1 bit. You need a special sequence. It's the same in our conversation. Our words, we need special words for communication. Okay, sometimes only short words are enough. But normally in communication, some words are necessary. And it's the same in RF communication. The data rate is a very important parameter because the data rate is the number of bits that are conveyed or proceed over per unit of time. That does mean when I need the time unit 1 second, for example, and I would transmit in 1 second 4 bytes or 5 bytes, sorry, 5 bytes, then I would have a transmission rate of 0.4 kilobits per second. If I would transmit in 1 second, for example, 20 bytes, then I have a higher data rate. So it means data rate means how fast the data will be transmitted over the RF channel. And a good example is I can speak very slowly, then I have a very, very slow data rate. And I can speak very fast and I have a very high data rate. That's the difference, yes? And that does mean when I have a high data rate, I can transmit many data over the RF channels in a very short time. And therefore it's important for an RF channel how much data rate I have. And on slide 13 you can see the data rate and the protocol are combined. This means the data rate is defined by the protocol. And here you can see, let's start with the 2.4 gigahertz data rates of the protocol, for example, Zigbee. Zigbee has a data rate of 250 kilobits per second. And for example, wireless LAN, we call it in Europe Wi-Fi, has a data rate 11 megabit per second and higher. Newest Wi-Fi systems have much more than 11 megabits per second. And here you can see with a Wi-Fi system you can transmit a much more data per second as, for example, with the Zigbee system. And then when you see the sub-gigahertz system, 868 megahertz, for example, ZF, we have only 75 kilobits per second. It's much more lower as the 2.4 gigahertz. And KNX is a very, very slow system. It has only 16 kilobits per second. And this is a great challenge for RF systems, because when you have a very low data rate, you need much more time to system to send out data. And time means energy for an energy harvesting system. We will see it later. So you see, data rate is a very, very important parameter for us. And data rate is combined with the protocol. And data rate is defined by the using microchip, because microchips have the data rate defined as a special parameter. So if you use a special microchip, for example, for Wi-Fi, then this microchip can use a high data rate. But if you use a sub-gigahertz frequency microchip, they only can support lower data rates. So it's defined by two things, protocol and also by the hardware of the microcontroller. And on slide 14, you see the data rate and the telegram length. Remember, different protocols have different telegram lengths. The data rate is the speed of the data, and the telegram length is the length of the word, defines the transmission time of one telegram. So if I want to transmit one telegram, it's defined by data rate and it's defined by telegram length. And for example, let's start with the first one, KNX. KNX has a very, very low data rate and has a very long telegram. This means to send out one telegram of KNX, you need 17 milliseconds. What does it mean, 17 milliseconds? Is it long? Is this short? When you see the other ones, then you see it's very, very long time. Because Zigbee, for example, has only 0.7 milliseconds, lower than 1 millisecond, to send out one telegram. Bluetooth, for example, has only 0.1, and Ocean 0.9, and ZF 1.3. So it means you can send out similar 16 or 15 telegrams of ZF in the same time as you can send out KNX. And that is a very, very, very big problem for telegrams with low data rate and long telegram length. And therefore it's so important for us what protocol we use and what data rate the protocol has and what telegram length the protocol has. Remember to this slide, it's an important slide. Depending on the protocols we use is the needed transmission time of our energy harvesting system. That was design parameter frequency, data rate, protocol, energy output, transmission time, many important parameters for the RF system. Another one on slide 16 is the designing of the antenna. You can create a very perfect RF system in hardware, in designing of microchip, designing of the PCB and everything. But when you make a bad antenna, then your complete RF system is bad. The antenna is a very, very important design parameter at the end of the system. And one of the parameters of antenna design is the length of the antenna. For example, when we're using a wiring antenna, as we used in our rocker switch or in our receivers, it's only a wiring, then the wire has to be an exact length, because the length determines the quality of the antenna behavior. And the optimal length of a symmetric, we call it dipole antenna. It means if you use two wires, then it would be an optimal dipole antenna. Yes? And using an optimal dipole antenna, the behavior or the performance of an antenna system is the category very good, I would say. Yes? And this is called a symmetric dipole antenna. So you would use two wires on your system. But you can also use a so-called unsymmetric antenna. So it's only one wire. On the other dipole is a ground plate on your PCB. And this is what we have, for example, in our rocker switch, in our module, in our snap switch, and also in our receiver. There is only one wiring, and the other pole is on the PCB, designed on the PCB. And the performance of such an antenna, we can say, is good. Not very good, but it's acceptable good. And the length of the antenna is depending on the frequency. And in the table below, you can see the optimal length to different frequencies. And you can see here, for an 868 megahertz or 950 megahertz, the antenna length is about 8 centimeters. And for a 2.4 gigahertz, it's only 3 centimeters. And this is, for example, another advantage for using the 2.4 gigahertz, because the designing of the antenna, they can be very shorter. And this is the reason why currently it's possible using 2.4 gigahertz system using such receivers, because there are inside very, very small antennas. No wiring antennas. These are chip antennas or SMD antennas placed direct on the SMD. But the performance of a 2.4 gigahertz antenna on such a small receiver is much more better as when you would use the 868 or 950 megahertz frequency. And that is the reason why this is another advantage. The antenna design could be more adapted to small housing. On slide 17, I listed, or there is the link to our basic information concerning interferences. Every RF system in the use case or in the real environment where in the application, yes, it has to be robust against interferences, because the more RF systems are installed in your application, the more RF interferences occur in this application or in these systems. For example, Wi-Fi. Everybody of us has a smartphone or a laptop. We have routers inside, so we have a high traffic of Wi-Fi communication around us. And if there would be no things inside the designing of the Wi-Fi systems against interferences, it wouldn't work. So in the Wi-Fi specification, for example, or in every RF specification, there are special things and special issues against the interferences, to avoid interferences. And in our application node, installation of our energy harvesting system, we described some restrictions or some informations for the user. He should have a look on it when he install RF systems. And one of the problems could be the damping of the radio waves inside buildings. because different materials have different damping categories. And here we have listed some materials which different damping categories. Yes, and you see, for example, wood or glass have a relatively low damping factor. It's about 10%. It's not so bad for an RF system. When you have bricks or stones, it's about 30, 35, 40% in this range. And if you have metal or metal grid, then you have a damping of 100%, because metal is the dead for an RF system. So it's very important when you discuss with a customer concerning the housing of the application, and the customer said, okay, he has a full metal housing, then you can say to him, okay, if you don't leave outside the antenna of the system, then it cannot work. It's very important. Metal is absolutely dead for RF system. When you cover a metal housing around an RF sender or an RF receiver, it couldn't work. So it's a very important information. Another issue is the installation guide, because yes, walls, bricks, or other damping objects, yes, has influence. So when you install your RF system in such a way that the damping is very low, then it's very good for our RF systems. So also you have to install your RF systems not on sender and receiver, not on the wall. The best way is to install it in the opposite of walls. Or interferences, also reflections or interferences can happen inside buildings. There is described in this installation guide. Yes, and also jamming, yes, could be another problem of other electronic devices. So the application note should give the customers a short overview what he should avoid or what he should consider when he installed an RF systems. But it's always the question of you cannot cover all environments and all circumstances of a real application. Okay, what we implemented in our RF system, one issue against interferences to other systems which are sending or transmitting on the same frequency, and this is the repeating of our subtelegrams. As I described, the ZF-RF protocol, or the ZF proprietary protocol, is about 12 bytes, and by pressing our sender or pressing our energy harvesting switch, we send out 3 telegrams. Every time 3 telegrams. And the time between the subtelegrams is not equal. It's random. It's a random time slot between the first and the second and the second and the third. And this should avoid when you install several senders in one surrounding, that the receiver gets always at minimum 1 subtelegram from one sender. It's not a 100% assurance against interferences, but it's decreased the risk of an interference and is of a collision of the telegrams. Because of a 100 assurance that every telegram comes to the sender, you cannot give. Because if you install 100 switches in one surrounding or in one application, then the risk of a collision decreases more and more, increases more and more. On slide 19, you can see a short overview of the necessary approvals. in Europe, in the US and Canada, and in China. So in different countries, you have to fulfill different regulations. And in every country, you have to do a different type of approval or getting the approval. In Europe, it's a declaration of conformity is necessary. But in USA, Canada, and also in China, you have to go to an official department and have to bring your documents, your test reports, and have to ask for an approval. That's the main difference between Europe and US and China. And you have to fulfill different regulations. But the most important thing is, when you want to sell an RF product in different country, you have to fulfill different regulation and have to ask for different approvals in every country. So, example, currently we are joining for the approval in China, and in parallel we have a customer question from a customer in Australia, and he wants to know if he can sell the product in Australia, and we have to say, no, you can't. You have to do an approval, a special approval to ask for in Australia. And the main task is when we want, and it's also the question, for example, for South America. When we have fulfilled the regulations for North America and USA and Canada, but we cannot sell the products to South America. Otherwise, we have to fulfill the regulations there, and we have to ask for an approval there. And I know a customer of a battery RF switch. It's a customer since 5-6 years, and he asked for approvals in over 140 countries all over the world. And he has an effort of over 500,000 euros to get all these approvals all over the world. So it's a high effort to get all these approvals. Okay, and on slide 20, I made a short summary of all the important parameters you saw. Remember, transmission range depends on frequency. This means the higher the frequency, the lower the physical transmission range. This is the advantage of the sub-gigahertz frequency, 915 for example, and the disadvantage of 2.4 gigahertz. With standard protocols like Zigbee, like Ocean, like KNX, you have the maximum flexibility because of there are receivers in the market. They understand the protocols. When we create a ZF proprietary protocol, we always have to offer the customer sender and receiver together. But when it is okay for customers and our sender and our receiver fits absolutely good in his system with a good performance, then it's okay. But if a customer said he wants to buy only a sender, but all the receivers he already has, or he has a great portfolio of receivers, of standard receivers, then a standard protocol would be better. The data rate depends on the frequency. Remember, high frequency means high data rate. Data rate is the speed of the data over the transmission channel. 2.4 gigahertz systems have very high transmission data rates. Wi-Fi, for example, very, very high. Zigbee, 250. And lower frequencies, like 915, has lower data rates. The protocol defines the data rate. This means data rate and protocol are combined together. And the data rate affects the transmission time. Remember, this was the diagram with a big KNX green time and the very short times of Zigbee or ZF. This means high data rate, or yes, low data rate means high transmission time. And the transmission time depends on our system efficiency, because when I want to reach a high transmission rate, I need high energy. But our energy is limited from our generator. So also the transmission time is limited. And the frequency affects the antenna length. This means the higher the frequency, the lower the antenna length. This means 2.4 gigahertz, remember? Yes, you can use 2.4 gigahertz with very, very slow receivers. And it's also a topic of our wiring. When we are using, for example, we would use a rocker switch with 2.4 gigahertz, then the antenna would be only in this way, 3 centimeters or so. And we have correctives, that's the word, I don't remember, correctives against interferences. One corrective is repeating of our subtelegrams. Another corrective could be installation guide. And some of the installation guides we described in our application note. Okay, thank you. That was basic information of our RF parameters and basic information for an RF system. Remember to the most important facts. Remember to frequency, data rate, protocol. It all depends together. And therefore, it's not so easy to design an RF system which covers all use cases and all applications in the big field of our customers. It's not possible. It's always a compromise.